A very good morning to all. So, thank you, Chaz, for giving and FOSS4G 2026 for giving me this opportunity. I'm Navinkumar, a PhD student from IIT Bombay, Department of Civil Engineering, under the guidance of Professor Dr. Raj Ramshankar. So, AutoICE is a standalone tool which being used for glacier ice peak estimation. So, what are glaciers? Just a brief outlook review. They are the freshwater reservoirs. They are the climate indicators which say how they melt, and then they give a lot of information about how the climate change is. And second one, they are the major place where the river flow is being maintained. At the same time, they store 75% of fresh water. And another recent study, they showed how these glaciers are contributing to people. If you see, they have given three perspectives: material, non-material, and also in regulation. So on top, you'll see the percentages, right? So water supply, agriculture, spirituality, and water regulation. So glaciers are like closely deep-rooted with people in these different dimensions. So that's why the glacier plays a very key role on water storage potential. So ice thickness is a very important key variable to find out how much, to assess how much glacier water is there, and also for the future data availability. Now, why glacier ice thickness matters? They help in understanding the glacier evolution, how the glacier is now and how it's going to be in future. At the same time, what is the global sea level rise when you are seeing a larger scale perspective. And they also tell the future lakes. Like for example, recently in Sikkim, there happened a glacier flood. A glacier outburst was there. So directly to the 20-kilometer downstream, a lot of big disastrous event has happened. And for that reason also, glacier ice thickness plays a key role to identify where the lake might form and how that potential will be at the downstream in the future. The last one is freshwater availability, which everyone has some idea about it. So after the next century, how the water is going to be from this glacier. These are all the information what we can get from this variable called ice thickness. And how to measure ice thickness directly? That's a traditional method. Ground penetrating data we use, seismic surveys we use. They are very accurate data in that research point of view, and they are used for calibrating and validation part. But the problem is, there are thousands of glaciers, in that only 1.4% of the glaciers are being monitored as a field measure. Now there is a serious lag in field data. That's why there are alternative ways, right? So we'll get into that. First one is empirical scaling relationships. They use a glacier geometry like area with some constants, and then they get the volume. That is like for 1,000 glaciers, what is the total volume? You can get from it, but it will not be in a spatial data format. This was used at the very beginning after the traditional method. Then came physics-based inversion models, a set of mathematical equations which has some physics laws behind it, and then we use model inputs and parameters, and this remote sensing data plays a key role in this physics-based modeling part, and then you get a spatially distributed ice thickness for each and every glacier. The next one is like the models. What we use are from simpler to complex. This being shallow ice approximation, hybrid models, higher order Foot-Stokes equations are there. It's like solving the number of unknowns. The simpler one solves a lesser number of unknowns, and the complex one solves a more number of unknowns. Now, for globally, when you say are the ice volume estimates are there, it is there. How they are being estimated? Using this shallow ice approximation models. Why? Because they are computationally efficient. They are simple model, but the results whatever we get, they are quite feasible to understand how much volumes are there in the current scenario. So there are three different types of approaches: mass conservation, velocity based, and shear stress based. Another one recent trending is machine learning. This is booming in all the domains, where you get a field data, and then you have a remote sensing data like debris thickness and what we have seen earlier. Another one is in many shallow ice approximate models, what we use, the parameters are assumed constant. Because it's very complex to collect the field data, as we have seen only 1.4% of data only are available. So they assume as a constant for more number of glaciers. And surface velocity data nowadays, Landsat, Sentinel-1 and 2, they are abundant, and surface velocity are also there. But still, this is not being used or directly implemented at the larger scale for ice thickness estimation. The last one is automation. Yes, they exist, but they have some problems. Like whatever automation is being done, they are connected with proprietary tools like ArcGIS, and then they work. But there are very few standalone tools which are being used for estimating ice thickness. At the same time, uncertainty is a key factor for identifying the model. If the model doesn't have a proper uncertainty, we will not be sure how accurate we are going to rely on the ice volume. These are not embedded in this automation part. That's a serious limitation. So, to address this, we termed a new model called velocity-based ice thickness inversion. This comes under the family called velocity-based shallow ice approximation. That means the major data what we use is surface velocity here. The scientific advances is nothing but the parameters as we discussed earlier. They were used as constant. Now we are using remote sensing data. Rather than using a constant, we will use remote sensing data and then address that part. So this is a typical model equation. First we'll show what are the remote sensing inputs we use. The one in red color is at the left side is surface, glacier surface velocity, and on the right side there is a surface slope that we use from the DEM data. Second one, what is the new thing that this model encounters is using a land surface temperature as a proxy for a parameter which says how the ice is pure or not in a general explanation. For that we use land surface temperature as a proxy. Thickness and measuring ice temperature throughout the glacier is very difficult. We call it as a proxy which is being used as a land surface temperature. Another one is basal sliding. Below the glacier there is a surface where the bed is there. How the glacier moves at the bottom is very difficult to identify. So people find it indirect ways to get this. And this one was the most prominent what we understood from research. So we are using winter velocity and annual velocity. When there is a winter in that colder region, there is no melt. So obviously there is no movement at the bottom. Four different glaciers. The one at the D is the Patio where we ourselves built our team and we collected GPR data. Other three are available in database, in Glacier database. I took that data and then we compared how the GPR observations, how our model is getting estimated. Now we can see the RMC is coming around 35 meter, and also the mean absolute error is 28 meter. Not big difference are there. Some systematic biases are there at the higher estimations, but the correlation is good, like R square is 0.64. So we believe that this kind of model is already working well. We have to make it automated. Now the problem is this model has assumptions. Because of this reason, we are not able to apply it for all the glaciers. There are different glaciers called thermal, polythermal and cold glaciers based on thermal design. This model works only on thermal and polythermal glaciers. Now how to use this to be scalable for other glaciers as well? For that we use AutoICE. That is open source tool. I mean the free software what we have made. So what this AutoICE does, it doesn't only automate the model, but it also adds the uncertainty component in it by default, where most of the open source tools are not having in the glacier ice thickness estimation. So we use a typical Monte Carlo method. The equation what we see is a nonlinear equation, and Monte Carlo method works very well in this nonlinear nature because we are giving distribution of data sets for each and every parameter. So what it enables is the automated part. The other part of non-technical part is they are done one glacier after another glacier it processes, and it's memory safe,
and also it's applicable for basin scale application. So people who don't have the knowledge on the basin scale, it's a particular watershed in which the basin is there. Within that basin, there will be something around 50 to 100 or more than 100 number of glaciers. So at a time, you can run this tool on 100 glaciers. That's what the meaning is. Another part is user controlled. Initially, when they make an automated tool, they restrict, okay, this is what the input you have to give. We are giving a little bit leniency, like you can change the data. You can use the data in such a way which is, I can tell this while explaining the GUI, so it will be more easy to understand. Another one is the fine tuning of the parameters is also done here. So the typical workflow, let us go fastly from left side to the right side. This particular code is written in R environment, and then we have used PyQt for a GUI generation in the front end. So the inputs are dim, velocity, annual surface temperature. These three are remote sensing data, and glacier boundary, which is in the vector polygon format. The other two information are winter surface and glacier cross section. They are optional. As I said, if some people want to do on other glaciers, these things are not necessary. So they go into the model input parameters where you get the slope, annual velocity, and other options. And then it goes into the model. The uncertainty and model are estimated at the same time. And then we are giving this an output. So in a research community, when you see the coding is being made, but well-organized output is not available. Most of them might have experienced this. The model will be good, everything will be good, but well-organized output is one factor where people is not able to understand. And I also face the same problem. That's why I thought we'll initiate this. And we made a separate folders for each and every output. And also we have given the non-spatial output also, which I'll explain clearly. So how the GUI looks like is very simple. There are 5 tabs. The first one says what is AutoICE. The second one is the model setup. Like you can give a DEM if you select it and give a DEM data. And then you give a parameter values here, and then you give a common parameter values here. If I start to explain, it will take a lot of time, but that's how the GUI looks like for the model setup. Another one part is uncertainty. We have taken the literature-based values and also what we have experienced from the field, and these parameters can be played. If the person is a glaciological expert, he can change the values for uncertainty and estimate uncertainty. Another one is help. We have made a very clear-cut PDF user manual for this, so people will understand how to use this tool also. And last one is the credits part, which who has done it, and some licensing parts as well. Now to know the status, we know the model is running, but if you are running for 1,000 glaciers at a time, you have to know the status, right? What is happening, at which stage it is. Is there any error in between? We have added this small display where all the informations are being stored. At the same time, lively it is be showing where the status is and all. So these all are the problem I faced while I was doing the research. That's why I have added this in this software. Next, we did this as a small basin level demonstration where we have selected 55 glaciers, which is in the Himalayas. So cross sections and the boundary are shown in the first one. It's a vector data. Another one is the DEM surface velocity we have given in 30 meter. The DEM and surface velocity spatial resolution determines the output of the thickness. If it is 30 meter, the output also will be 30 meter. The input is 15 meter, then output will be 15 meter. That's how we have determined. But land surface temperature is it can be of any spatial resolution, because in the end, only one value is going to be used. Now, the important and clear-cut part is you don't have to give 50 separate inputs. You just give one DEM for this one particular full region, surface velocity fully, and also the boundary fully. Once you give it fully, it will automatically arranges itself, and then it will execute the ice thickness for each and every glacier. So, as I said, there are 4 different folders. 3 folders contain TIFF file, like spatially distributed ice thickness, bed topography, and also the uncertainty in a spatial distributed format. Another one is the map. Like some people who are working in agencies or who wanted to know how the glacier ice thickness is at that moment itself, it will automatically generate like this. What is the ice thickness, spatially distributed information, what is the area, and how much the volume is, what parameter that are being used, and what are the estimated parameters as well. Finally, as I said, not only spatial output, we are also getting in an Excel sheet in a very clearly understandable one. That's the information. We generate unique glacier ID for based on that centroid of the glacier. Also, we get the mean, maximum, and minimum of the surface elevation and glacier area and all the information. At the same time, show how much time does it take to execute for one glacier, so the user can understand, how much it is going to take. So the computation time when you use uncertainty at 30 meter resolution, the very recent one, the Ultra Intel processor, it will take 1 hour for 77 kilometer square of area. If you don't use uncertainty estimation, directly it will give in 15 minutes. For example, in a standard system, you have 1,000 glaciers. Within a week, you'll get all the spatial distributed output. So these are all the results that we use for interference for in future for other applications what I have discussed. The limitation is, since this model is based on an assumption, it doesn't work on fast flowing or such type of glaciers, where within a shorter period of time, the glacier moves very fast. That this model is not applicable. And the uncertainty, we have just used an independent type of selection, that is Monte Carlo. In future, there has to be a statistical dependence, which will give more relevant to the model. And the next one, this AutoICE is best suited for the glaciers between 500 to 1,000. Like that, you can keep on estimating it. So when you use this on the other glaciers, it will work, but it will have uncertain data, or you have to be very cautious on understanding the data as well. So this is a free software. Right now, we have submitted the manuscript, and it's on the review. This tool is Windows-based OS. It is available in GitHub under password protection. This relies only on remote sensing and GIS inputs. And the code is also easily understandable with proper GUI. You can also find this research paper what we have done in this preprint under Navinkumar and Ram Shankaran. And this is my supervisor, and that is me. And for front end, we have taken the help of interns. So if they are interested or have wanted to give any inputs from the problem what you face on the glacier point of view or anything related to Glacier, please contact us. Thank you.
For a nice presentation, a useful presentation, and particularly in Indian context, it seems very much relevant, because in past few years we had very severe flooding problems in the Himalayan region of India.
True.
So a good work. And now the session is open for the question answer.
Yes, sir. Yes. Yes, sir. Very true, sir. Yes, we have looked into it. Now the problem is, when we wanted to know the physics informed neural networks, you have to understand the physics very well. Now the physics model itself is in the growing stage. Unless and until we don't fully bring out the full potential of physical model, it will be difficult in physical informed neural network. Yes, sir. Yeah. I have studied even from Switzerland. Team has also done very good research on this physics informed neural network. At the end, they have given a small caution also. Yes. So what they have said is, though this model works very well, it needs field data to understand. But you can see only 1.4% of data is there. Remaining, you have to assume and then do. Rather than doing an assumption and getting the output, you have a physics laws which have some science background behind it. We can rely on it more. But definitely in future, what you are saying will be the forefront, sir. Yes. Thank you, sir. Sure, sir. Yeah. DEM I use for surface slope generation, sir. For surface velocity, we use data from a Landsat from period 1 and period 2. For 2017, on October, I take one image. Same on 2018, I take another image. I do a feature tracking, and then I find out the surface velocity, sir. The DEM what is used is for SAR data. Synthetically aperture data, you use DEM data for correcting it. That is different part. I have used optical data here. Optical remote sensing data. Yes, sir. Correct. You're asking how this glacier thickness will be helpful for GLOF? Yeah, as I have said, the ice thickness you have got. Now, if you take a dim of any data, you subtract this with ice thickness, you get the bed of the glacier. Now, there is a term called over deepenings. There is a normal surface and there is an over deepening. So when the over deepenings are of certain standard, there is a certain standard in GLOF definition. If you follow those standards, you will identify, yes, this particular place, if it melts after 2 years or 3 years, that kind of lake will be formed, which can be a potential one for a future glacial outburst. Existing glacial lakes, you will be using DEM elevation only. Generally, that much is sufficient to see how the lake is being grown up. At the same time, the velocity is also used. We say it as proglacial lakes when there is a lake which is connected with ice. If it is not connected with this ice, it's a normal glacial lake. So to monitor it, ice thickness will be one of the input, but it depends on ice thickness, surface elevation change, and although the local temperature and precipitation data. Yeah, yes. Volume means you have a glacier, full glacier, 77 kilometer square of glacier with 30 meter pixel, right? So you take sum of all those with the 30 into 30 meter and the ice thickness, you get a total volume of the glacier when you sum it all. That's how you get ice volume for the glacier. Yes, sir.
Okay, so Bowan, maybe we run out of the time. Maybe you can talk to the presenter after this one. Okay, very nice presentation, and then we will go to the next presenter. Yeah. Thank you very much.
Thank you for being interactive, and thank you for this opportunity. Thank you.
Okay, so we didn't have the